So if we know that the internal energy is equal to Q, or is defined as Q for a reversible system, plus the work of a reversible system, that is equal to U, which is the internal energy, then du is equal to dq rev plus dw of a reversible system, or the reversible work done by a system. And if we know that dq, or the heat transferred for a reversible system, I don't know what I'm doing, w is equal to T ds, then we also know that, and in addition, we also know that d work for a reversible system is equal to the negative pressure dV. Then we can then have du is equal to T ds minus P dV. And if we said the enthalpy of a system is defined as U plus PV, then dH is equal to du plus PdV plus VdP, then dH is also equal to, where we plug this in for du, so this is going to go right there, then we have T ds minus P dV plus P dV, and those two cancel out, plus V dP. So these cancel out, so then dH is equal to T ds, or the temperature with respect, or entropy, plus, or it's the temperature times the infinitesimally small change in entropy, is plus the volume times the infinitesimally small change in pressure, dP. So then we have that. And what are we going to do with that? Well, we're actually going to take a break and we're going to go do something else. And this will get us the Maxwell equations. Maxwell equations. So if we had something that said dF, or if we had function f, and it was x, y, then we're not even going to worry about it. So what would that be? So if we had to take df, well then it would equal the partial of f with respect to x, but we'd have to hold a y constant, dx, plus the partial of f with respect to y, holding x constant, dy. Now we're going to do something a little bit funky. We're going to call this part m, and we're going to call this part n. So then we get a new equation that says df is equal to m dx plus n dy, and that looks like this equation, kind of. But more on that later. We'll just continue on with this. So now, for the fun of it, we're going to do, so I said m was equal to the partial of f with respect to x holding y constant. So if we were to take the partial of m with respect to y holding x constant, what would we get? We would get the second derivative of f, or second partial derivative of f with respect to x and y. And of course that's x holding x and y constant, but that just cancels out. So we'd get that. So if we did the same for n is the partial of f with respect to y holding x constant. And if we took the partial of n holding, or with respect to x holding y constant, we would then get the second partial derivative of f with respect to x and y. So if these equal each other, then that means these equal to each other. So then if we had the original equation, dH is equal to T ds plus V dP, and we said that this was M, this was N, this was X, and this was Y, and we plug that back into these suckers, what would we get? We would get that the partial of T with respect to pressure at constant entropy is equal to the partial of V with respect to entropy at constant pressure. Those two equal each other. And that is the Maxwell equations. That's what all this work was, just to say that these equal each other.